All right, welcome. We're going to try to do a little bit of basic forklift electronics, do a little video on that. This would be interesting probably for anybody that wants to learn a little bit about just basic electronics in general. We're going to talk about, let me go back here once. We're going to talk a little bit about basic atoms. We're going to go over some Ohm's law, which correlates voltage, current, and resistance. I'm going to talk a little bit about simple insulators and conductors, short circuits, open circuits, series circuits, and parallel circuits. Pretty basic stuff. If we start at the beginning, there's two basic particles of electric charge. One would be the electron, which is negative polarity. The other would be proton, which is positive polarity. Now, it is the arrangement of these electrons and protons that determines the electrical characteristics of all substances. And when we talk about electrons and protons, we're talking about atoms, of course. So again, the electrons and the protons and the neutrons and the atoms, the way these particles are arranged determines whether they're insulators or whether they're conductors. So a conductor allows electrons to flow easily through it. And it's basically electrons that actually give us current or give us electricity. An insulator holds electrons in place with little or no movement. Electricity is basically the movement of electrons through a particular substance. So now this is a very rare picture of an atom here. Of course, it's not really, but actually there is an atom there, but you can't see it, right? We can't really see atoms because they're so small. So here's a basic picture of a very simple helium atom. You can see we have electrons around the outer edge. We have basically orbiting around the outside. We have protons and we have neutrons. Notice we have an equal number of protons, equal number of neutrons, and an equal number of electrons. Now here's your simplest atom, which is hydrogen, which actually only has one electron and one proton. So what does all this mean? Well, there are basically shells, and electronics is sort of a science. So it does follow certain rules. So when we're looking at atoms, we have a nucleus and we have several different orbiting shells. Now there is a law basically to these atoms. I don't know who came up with this or how they figured this out, but in the first ring you can have two electrons, and now all these outer shells are going to carry the electrons in the atoms. The neutrons and protons are inside, stationary. So the first ring will be 2 electrons, then 8 electrons, 18 electrons, and then again 8 electrons in the outer shell. So if you have an atom with 3 electrons, you're going to have 2 electrons in this first shell, and then 1 will carry over into this shell right here. So let's take a look at another atom, which is copper. Now, copper has a number of plus 29, which means that it has 29 protons, 29 neutrons, and 29 electrons. So you can see here what we've done is we've put the electrons in their orbits, and you have 2 in the first shell, you have 8 in the next shell, and you have 18 in the next shell. Well, we have got 1 left over, all right, to add up to 29. That would be your outer electron right here. Notice it's the outside electron. It is the only one in that outer shell, okay? So we've put all our electrons in our normal shells there, and this outer little lonely electron was what we call a free electron. All right, that electron is basically free to move from atom to atom, and this is really what gives us electricity, the movement of electrons. So let's take a look at magnets. You know that likes repel. If we put two south poles together, they push away from each other. And if you put two opposites, a north and a south pole together, you'll get an attraction, right? They attract together. Well, electrons and protons are the same way. If you put two positives together, they push each other away. And if you put a negative and a positive together, the opposites do attract. So let's take a look at a regular copper wire. You have lots of free electrons, basically. This is copper, so we have one little free electron right there, sitting there in each one of these. But if this is just a regular copper wire, you have atoms just inside the copper wire, and you have those free electrons, and basically those are just maybe going to bump from one atom to another, but it's going to be random. There's not going to be any specific movement to those electrons. So now what we need to do is we need to put some sort of voltage potential across this wire or across this circuit so that we actually get electrons to flow. And what we're doing is we're actually pushing the electrons, those free electrons, through that wire, giving us an electron flow or current. Now here's our negative side of our battery. Here's the positive side of the battery. So our voltage or our battery is our electrical pressure right here. And what we're doing is here's the negative side. So what it does is that negative pushes those negatively charged electrons through the wire, and is basically the negatives are then sucked back through to the positive side. And you basically have current flowing now through the wire and actually through the battery itself also. The battery itself is made up of several cells depending on what size battery it is. If one of those cells would be open, you would not get any current flow. It has to flow not only through the circuit itself, but through the battery itself. So you have negative here, pushing electrons through your wire, through your circuit, and the positive actually pulling those electrons back through, so you have a complete circuit. Now, normally what we talk about is conventional current flow. And if I go back just once here, if I go back to this one again, you'll notice the electrons or the current flow here we're showing going from negative to positive. Now, if you're over in Europe, if you're overseas, they go by electron flow, just the way we're showing there. In the U.S., we go by more conventional current flow. We actually go by what we call hole flow, so that every time an electron moves in this direction, an actual hole moves in this direction. It's the empty hole where that space, where that electron was, is that space. So what we're going to talk about today is we're going to go with conventional current flow. Our current is going to be flowing from positive to negative instead of negative to positive. And that's the way we do it in the USA anyway, whether that's right or wrong. That just seems to be the way we do it. All right, so we're going to use some very simple circuits in this training video. You can see we have, we're using some symbols. This is a standard battery symbol right here. Each one of these would be a cell. You have positive and negative of your battery. And here we have just a little lamp. All right, so we have a complete circuit here. So we have our conventional current flow from positive through the lamp, through the circuitry, through the wiring to negative of the battery, in a complete circle like that. Our electron flow is actually in this direction, following the blue arrow like this. Now we're going to talk about conventional current flow and not electron flow. So our current flow is going to flow from positive to negative. So let's look at some insulators. Insulators are materials with atoms that have few or no free electrons. Okay, that free electron out there is the one that is able to move from atom to atom very easily. And it basically allows us to get current flow. An insulator has atoms basically where all those shells are full, so that you don't have any free electrons moving. Materials with very high resistance, and we'll talk about resistance then, they actually resist current flow. So a couple of examples of good insulators would be air, of course, glass, rubber, and paper, and those are pretty typically, most people would know that those are pretty good insulators and do not conduct current. Now, all insulators have some form of a breakdown point. Air, you need about 20,000 volts to break over an inch of air. So if you have an air gap, you would need 20,000 volts to actually jump across a 1-inch gap. Paper is about 1250 volts per 0.001 inch. So not much there. All right, so let's take a look at some conductors. Conductors are materials with atoms in which electrons move easily from atom to atom, just like the copper atom that we looked at earlier, where it has that free electron and it's able to actually move that electron through the circuit. All right, materials with very low resistance, little or no resistance to current flow. A couple of examples, of course, would be your metals, silver, copper, gold, and aluminum. Okay, those are all good conductors. So all materials have some form of resistance. The longer the wire, even if it's a copper wire, it's a conductor, but the longer the wire, the higher the resistance. The thicker the wire, the lower the resistance. So let's take a look at some examples of that. If we just look at a copper wire, we know a copper wire is very good conductor. It has that free electron to allow current to flow through it. So if we look at a 1 gauge wire, that's very, very large wire that we use normally in a forklift motor application, something like that. You've got like 0.1264 ohms of resistance per 1,000 feet, which is very, very little resistance. But again, the longer the wire, the more resistance you're going to have. So a 22 gauge wire per 1,000 feet is about 16 ohms of resistance. So it's negligible. It's a very low resistance, but you do get some resistance depending on how long that wire is. So let's take a look at our 3 basic electrical components. We have to have, for a complete circuit, basically, we need voltage, of course. Our voltage is considered our electrical pressure. Our current is basically what's going to do the work. The current is basically the flow of those electrons through our circuitry. And we do have to have some form of resistance just to maintain control, basically, of the flow of those electrons. If we had no resistance at all, we would have full current, and basically you're going to get either melting wires, burning wires, frying components, blown fuses, so on and so forth. So there always has to be some form of resistance in our circuit. So with all 3 of those components, that basically equals a complete electrical circuit. So let's first take a look at one of our components is voltage. Voltage is what we call our electrical pressure. It can be alternating current, which is basically our AC waveform that would be our household 120 volt in the USA anyway, voltage. But most of what we're going to do in this class is we're going to talk about DC, or direct current, which is supplied by a battery. And that's, of course, what we use in our electric forklifts. Now, the electronic symbol for voltage is E, for electromotive force. And this is our typical battery symbol, of course. Anytime you look at a schematic, forklift schematic, or any type of schematic that's using a battery, it'll show this type of symbol. Now, in order to measure voltage in our circuit, the voltage is dropped across components. So we're going to take our meter, and this is our, what we call, this is our load. This is our resistive load. Remember, we have to have some form of resistance in our circuit. So in our circuit, here is a contactor coil. It provides very small load, typically maybe 20 to about 40 ohms of resistance. So here is our resistive element, and what we're going to do is we're going to measure the voltage drop across that coil, and we're going to put our negative lead here and our positive lead here, and we will measure the voltage drop across that particular component. So voltage is dropped across components. Now, again, we're going to talk about conventional current flow, positive to negative, actually the whole flow. Okay, this is our electrical pressure. Here's our voltage right here. So as we increase voltage, we increase our current. So as we increase this voltage pressure or electrical pressure, say a 12-volt battery is going to flow a lot fewer electrons, do a lot less work than a 36-volt battery. So the larger our battery, the higher the voltage, the higher our electrical pressure, the more work we can do. Now let's take a look at current. Current is the amount of electrons flowing. Remember, it's what drives, what turns on our lights, what runs our TV, what drives a forklift. You know, a 5,000-pound electric forklift basically is operated by the flow of something we can't see, electrons. Okay, it's the flow of electrons. So the amount of electrons flowing is expressed in amps, or A for short, of course. Conventional current flow, again, we're going to talk positive to negative. Now, our electronic symbol is I for intensity. Right? And this would be our current flowing through the circuit here. Notice we don't have any sort of resistive load here, so we would get full current basically in our circuit, and we would basically melt any wires here. I don't care how big they are, they're going to melt with a 36-volt battery on here with full current. So that just shows we've got to have some form of resistance. Now, voltage, if you remember, is dropped across components. Current actually flows through components. So if you want to measure current, what you have to do is actually break the circuit, connect our volt-ohm meter up, set on current, of course, and you will actually basically set our meter in series with our circuit so that the current basically will flow through the meter, back out, and through our circuit. So the meter becomes part of our circuit, and that's how you can measure the current. Now, there's other ways. You can use shunt meters to actually break the circuit and put a shunt in here and put a meter attached. There are, for forklift applications on the very high current, there are clamp-on amp meters that you can basically clamp right on a heavy wire like this, and it will measure the current actually through inductance, what we call inductance, measure the current flowing through the circuit itself. All right, so our last component here to make a complete circuit is resistance. Resistance opposes the flow of current, expressed in ohms, or some use the omega sign. The electronic symbol is R, that's easy, for resistance. All right, so here we have a complete circuit. We have our battery, which is our electrical pressure. We have some form of electrical load to provide some form of resistance. And we have a regulated current flow now through our circuit, through our lamp, through our wiring, and back through the battery itself. So resistance comes in many values. Obviously, you can have tenths of an ohm, you can have a million ohms, but basically the omega sign, resistance equals ohms. All right, so let's take a look at some Ohm's law. These are formulas that we usually use in electronics. Just using these to basically show you the relationship between voltage, current, and resistance. So let's take a look. We've got an Ohm's law resistance, and we have a little circuit here. We have a resistor here. This is just a little symbol of a resistor right here. And we have voltage, where our E is 20 volts. So our battery voltage is 20 volts. Our ammeter is basically measuring 1 amp of current. So what we want to know is what's our resistance value if we have 20 volts and we want 1 amp of current flowing through our load. Now this load is just shown as a resistor, but it could be, any sort of a load. It could be a motor, it could be a coil, it could be a TV set, it could be, a forklift, it could be any sort of fan, any sort of resistive load. So Ohm's law, one of the formulas is ohms, or resistance, equals volts divided by amps. So let's plug in our figures. We have R for resistance, E electromotive force, I intensity. We plug in our numbers, 20 over 1 amp equals 20 ohms. So if we have 20 volts of electrical pressure and we have 20 ohms of resistance, we're going to get 1 amp of current flowing through our circuit. So resistance opposes current. Right? So we have our voltage here. We have a little bit of a choke, so to speak, in our wire, and it reduces or opposes the amount of current flow. So the higher the resistance, the lower the current. So let's take a look. Here is another little circuit. Here again we have 20 volts. We have our same 20 volts of electrical pressure. Now we've added a resistor in here. We've added a 10 ohm resistor. So let's see what kind of current we have. What we've done is we've reduced the resistance, right? Our last formula, we had 1 amp of current flowing through 20 ohms of resistance. So we've cut our resistance in half. So let's take a look. Here's our Ohm's law formula for current. Amps equals volts over ohms. Let's put it in. Here we have intensity, E over R. We put in our figures, 20 volts divided by our resistance, which is 10 ohms. And now we're going to get 2 amps of current flowing through the circuit. So you can see if we cut our resistance in half, we double the amount of current flowing through the circuit. Okay, so you can see resistance opposes current. The higher the resistance, the lower the amount of current that's going to flow through our circuit. All right, let's take a look. If we have 10 ohms and let's say we up our voltage to 50 volts, what do you think is going to happen there, right? That's pretty simple. We've got more electrical pressure to move more electrons with the same resistance. What do you think? Of course, we're going to get higher current. We plug in our figures. Here is our intensity. We have 50 volts, 10 ohms. We get 5 amps of current flowing through our circuit. So again, as we increase our voltage, our current also increases. All right, so we can do it a number of ways. If we increase our resistance, we reduce the current. If we lower our voltage, we'll reduce the current. If we increase our voltage, we increase our current. If we increase our resistance, we reduce the current. Okay, so they play off of each other. Okay, so here is here's our Ohm's law voltage. All right, so here if we have 1 amp of current flowing and we have 100 ohms of resistance, we use our voltage. Our volts equals amps times ohms. We plug in our numbers. If we have 1 amp, and that's not shown here, but let's say we have 1 amp of current, well, what is our voltage that we need to push 1 amp of current through 100 ohms? And basically, we're going to need 100 volts of current to push 1 amp of current through 100 ohms. All right, so one more formula, Ohm's law power. Okay, the actual power, watts equals volts times amps. All right, so our actual power is basically a combination of both voltage and amps. So simplified would be power equals electromotive force times current. So let's take a look. If we have 12 volts and 100 amps of current, we have 1200 watts of power. If we double our voltage, we double our wattage. Okay, we double our power. So again, in forklift application, in your small walkie truck, you may have a 24 volt battery. So if we double the battery voltage, we can double our wattage. Right? We can get more power. If we double our current, we double our wattage. Now, in a forklift application, 746 watts of power equals about 1 horsepower. So that's the way they rate their electric motors in a forklift application. All right, so let's take a look at a simple circuit here that we have. Basically, we have 60 volts of electrical pressure. When we have 4 different values of resistance. We have a 20 ohm resistance, we have 30, 60, and 10 ohms. So now these are just resistors, or these are some form of resistive load. They could be a motor, they could be a lamp, they could be a fan. Basically, we have resistors in series. They are tied basically to each other in this basic circuit. So our current is going to flow through all 4 of those loads, okay, at the same time, and through our battery. So now if we basically, this battery here is going to look out, and it's not going to see 4 individual loads. It's going to see, if you add up these resistors, you're going to have a resistive total of 120 ohms of resistance. Now, if we use our formula, our current equals voltage divided by resistance. Our voltage is 60. Our total resistance is 120. So we equal 1/2 amp of current. So here we have our 60 volts. We are going to push 1/2 amp of current through that entire circuit. We're going to have 1 amp of current here. We're going to push 1/2 amp of current through our circuit. So we're going to measure, we can measure here, we'd have 1/2 amp of current. If we measure here, we'd have 1/2 amp of current. If we'd measure here, we'd have a 1/2 amp of current all through this entire circuitry. So now what I want to do is, let's take a look at the voltage drops through this circuit. we can check our voltage drops. Here's our voltage, our current, here's our 20 ohms of resistance. So we're gonna figure out what the voltage drop is across each one of these resistive loads. And we're going to use Ohm's law. So E equals I times a resistance. So that equals 10 volts. All right. So we get a 10 volt drop across our 20 ohm load. Now, if we use the same formula, E equals I times R, we get 15 volts dropped across that resistor. And we continue on again, our 60 ohm load. We use our Ohm's law formula and we get 30 volt drop across our 60 ohm load. And across our 10 ohm load, we get 5 volt drop. Now notice here's a 20 ohm load, it drops 10 volts. 10 ohm load, it drops 5 volts. Okay. Our 60 ohm load drops the most voltage because it's going to resist more current and it's going to drop more voltage. So basically, if we look and we add up all these voltages, we basically add up to 60 volts. Okay? So our voltage drops across all of our loads have to add up to 60 volts. So 10 plus 15 plus 30 plus 5 equals 60 volts. So let's take a look. If you're going to measure, do some measuring of voltage, let's say we're going to use our negative as a reference. If we would reference our meter to this point here and measure the voltage at this point here, we would be measuring the voltage drop across this resistor right here. So our voltage drop would be 5 volts. If we measure from this point here, from battery negative to this point over here, we're going to be measuring the voltage drop across the 60 ohm and the 10 ohm. So we're going to get 5 plus 35, or plus 30, we would get 35 volts drop right here. Okay, and we can do that all the way around the circuit. But the key here is we are going to get voltage drops to add up to the voltage we're being supplied. Now, what happens in this circuit? Let's say we have a poor connection right here. All right, let's say we've got a poor connection right there. Maybe it's a corroded connection. Maybe it's a wire partially broken, something like that. What we're going to do is, if we have a poor connection or a connection that's not tight, it's loose in a nut and bolt connection or something like that, what we're going to do is we're going to actually provide resistance at that point. That resistance is going to oppose current. That resistance is going to oppose current and actually create a voltage drop. So if that creates a voltage drop there, that means that voltage drop has to also be part of that 60 volts. So if I have a poor connection here that drops, say, 5 volts, that means all my other resistive elements, fans, motors, whatever, are going to be reduced in voltage because of this added voltage drop, because they all have to add up to 60 volts. So that's the kind of problem that we have with a poor connection. Okay, we're also going to have an added resistor here, so our resistive total is going to be more, so our current is actually going to be reduced because there's an additional resistive element. All right, so here you can see 10 volts, 15, 30, and 5 volts. Again, measuring the drop across this resistor is 5 volts. We always measure from battery negative. While I have this circuit on here, you always want to reference to battery negative. Basically, wherever you put your battery negative lead, you're saying is 0 volts. and anything you measure is going to be then positive. So let's take an example. If I put my negative lead on battery negative and measure this point here, which is basically right across the battery, I'm going to measure 60 volts. And I'm going to measure positive 60 volts. Now, what happens if I put my negative lead here on battery positive, which basically I'm saying this is going to be 0, and I measure this point here, what I'm going to measure is negative 60 volts. Okay, so you always want to use, well, 99.9% of the time anyway, you want to use battery negative as your reference. Anywhere you put your battery negative lead, you're going to say that's 0 volts, and everything else is going to be positive all the way up through the circuit as you measure your voltages. All right, just a little break here. Which is larger, right? It's not an optical illusion. The circle is actually smaller than the square. Okay. All right, so a complete circuit we've talked about. We need our voltage source, which is our battery. We need our load and some form of resistance to regulate our current. And we need complete connections between the source and the load. So here is our complete circuit. We have our electrical pressure. We have a resistive load. We have a regulated current flow through it. Okay, so now what we could do also, we could measure the voltage drop across that lamp. We can put our meter right here. All right, this will be anywhere along this path here is going to be basically 0 volts. All right, because we're going to use this as our reference. Anywhere on this side of the lamp is going to be 36 volts. So if we measure the voltage drop across that lamp, it's going to be 36 volts. So we need a 36 volt lamp in our circuit. Okay, we have our voltage source, electrical pressure, we have our load, and we have connections connecting our load to the battery itself. All right, so let's take a look at a couple of different circuits. Here's an open circuit. This is pretty obvious. We've put a switch in our circuit here. This is a standard series circuit. Everything is connected together. All right, so our 36 volt battery, we have our lamp off because there's no current flowing because we have a break in the circuit right here. We don't have a complete circuit. Electrons cannot flow all the way through. Now, if we would take some voltage measurements, basically, if we reference our meter to battery negative, we measure from battery positive, this would be 36 volts right here. On the other side of this lamp, we would also get 36 volts. 36 volts we would measure all the way down to this point here where there's an open. Voltage has a tendency to float all the way through a circuit until it can't go any farther, which would be right here. So if I have 36 volts here at this point and 36 volts here at this point, that means my voltage drop across the lamp is 0, which is correct, and the lamp is off because we need some form of voltage drop across it to basically power it up. All right, so here is basically a short circuit. We certainly don't want to have that. Here we have somebody's put a switch in the wrong place and basically shorted out the battery itself. No resistive load. You've got full current flowing with a big forklift 36 volt battery. These wires are just going to start to melt. You're going to let the smoke out of them and everything's going to burn open. Okay, so we don't certainly want to do that. So we've talked about series circuits. Series circuits basically are where current is the same throughout the circuit. Voltages add up throughout the circuit. So let's take a look. Here's our standard series circuit. And we have a 36 volt battery. Now we have 2 lamps. Okay, so 2 lamps in series with each other on a 36 volt battery need to be 18 volts because each one of these lamps, if they are equal in resistance, they will share the voltage drop throughout the circuit. So we'll have an 18 volt drop across this lamp. We'll have an 18 volt drop across this lamp. 18 and 18 equals 36 volts. All right? So we can measure from battery negative to this point here, and we'll measure 18 volts, which is our battery voltage or our voltage drop across this lamp here. Okay, we have regulated current, voltage drop across each 18 volt lamp. Now, if we put 3 lamps in series, they have to be 12 volts, right? 12 plus 12 plus 12 equals 36 volts. So we have a 12 volt drop across this lamp, 12 volts across this lamp, and 12 volts across this lamp. Again, if we were to reference to battery negative, we would measure 12 volts at this point. We would measure 24 volts at this point. Okay, that would be measuring the voltage drop across both of these lamps. Okay, we always want to measure through the circuit, not through the battery itself. Okay, so we're going to measure from here through the circuit to this point right here. Okay, that would be measuring the drop across this lamp and the drop across this lamp. Okay, now in a series circuit, we're back to 2 lamps. The current is going to remain the same throughout a series circuit. All right, so again, if I measure the current here, it's going to be 1 amp. If I measure the current here, 1 amp. If I measure the current here, 1 amp. I know this is basically, we reference this point here, and we're going to say it's 0 volts. But basically, we still have current flowing through that line. And remember, if we reference our meter to battery positive, this is actually negative 36 volts. Okay, so current is the same throughout the circuit in a series circuit. Let's take a look at a parallel circuit. In a parallel circuit, current splits between all parallel paths in the circuit. The sum of each branch will add up to the total current being supplied by the battery itself. The voltage is equal across all parallel paths. Okay, so let's look at a simple parallel circuit. We have our 36 volt battery, and notice these lamps now are tied basically both directly across the battery. This lamp is tied to the positive side and also the negative side of the battery. This lamp is tied to the negative side and the positive side. So here we're going to use 36 volts lamps because each lamp is tied directly across the battery in a parallel fashion. Okay, so 36 volts. Each lamp will have a voltage drop across it of 36 volts, which is equal to our battery. Now, in a parallel circuit, the current will split so that you'll have a current path through this first lamp, through the battery, circulating right through here, and you'll have a second current path flowing through this second lamp. Okay, now these currents will of course add up. So let's say we need 1 amp of current to flow through this lamp, and of course we will need 1 amp of current to flow through this lamp. We need then 2 amps flowing in this line here. Okay, 2 amps flowing that will break off and supply both of our lamps. So if we would break the circuit and we would measure the current here, we would measure 2 amps. If we'd break it here, we would measure an amp. Over here, we would measure an amp. Down here, we would measure an amp. Over here, we would measure the total of 2 amps flowing back through the battery and out. All right, so that concludes just a simple basic video of series and parallel, and a little bit of Ohm's law. So I hope that helps you a little bit, on some things. Pretty short video. I'll try to do a couple more videos with some basic electronics and maybe delve into a little bit of forklift parameters also. Okay, have a good one.